Welcome to Calculus. Today we will investigate function continuity, focusing on using the three criteria in the continuity definition to justify why a given function is continuous or discontinuous. Let's take a look at the definition and two examples. In our previous segment, we looked at two examples where we saw different kinds of function discontinuity. But at some point, we need to define what makes a function continuous. So we'll begin our first two examples on this segment with that definition. So here is how we would define a function as continuous. A function f is continuous if three things are true about the function. So let's name those three things. And I want to actually refine this. A function f is continuous at the x value when x equals some number a. So the three criteria are as follows. Number one, we have to say that the function is defined at that x value. So what we'll say is that f at a exists. The second criteria is that the limit as x approaches that specific number a from the right and from the left exists and is defined. The limit as x approaches a for this function f of x exists. Can you anticipate what the third criteria is? Really, we're going to pull those two first criteria together. And what we're going to say is that that value of the function at a must equal the value of the limit as x approaches a from both sides of the function. So that gives us a real clear and specific definition of continuity. Let's take a look at two examples and use that definition to decide, should we classify the function as continuous or discontinuous? And if it's discontinuous, why? Which of the criteria does it contradict? So here we've got the function f of x equals x cubed minus 2x squared minus 1. And I do want to see that function graphically, so I want to graph it by creating a table of coordinate points. So I'll create the t-chart. And I'm going to use the graphing calculator to come up with this table of values. I definitely could just choose some x values and then plug them through the equation and calculate y values. But I think our focus here is really on seeing, is it continuous or not? So I'm going to write that function down and I'm going to plug it into the Desmos calculator, x cubed minus 2x squared minus 1. So let's head over to Desmos. So we'll enter that function f of x equals x cubed minus 2x squared minus 1. And there's our function. So I do want a table for that. It looks like if we chose values from about -2 through maybe 3 or 4, that would give us a good slice of that middle wrinkle in the cubic function. So I'm going to extend this to 3. And let's also give 4, so it automatically provides it for us. And I'm going to record those values. So at -2, we have the y value -17, -1 is -4, 0 is -1, 1 is -2, 2 is -1, 3 is 8, and then 4 will be off our graph. I'll record it. It's 31. Let's head back and complete our table and our graph. So I'll put those x values first. We went -2 through 4. And again, those y values or f of x dependent values are -17, -4, -1. And then the function dips back down, -2, back up, -1, and up, up, and away into the sky. So we've got our table, and I want to graph that function now. So -2, -17 is off my graph. -1, -4, however, is there in quadrant 3. 0, -1, that's my y-intercept. 1, -2 is where it dips back down again. 2, -1's where it rises up. And then 3, 8, right on the border, upper border of my graph. And then 431, again, ungraphable. So I'm going to sketch this cubic function. And as I sketch, we want to consider, is this function something that we could call continuous, or does it break one of our criteria? So just to remember, the definition of continuity is based on a certain x value. So if we've got function f, we're really considering when x equals a specific number. So let's just investigate, kind of considering all these points on this purple function. So at x equals a, for f of x, these are the things that must be true. F at a must exist. So as I look at that graph, I see that any x value that equals a number is defined in the function. And I can really see that in all these y values. There's nothing in terms of an x value that would be undefined for this cubic function. So it seems like we're good there with that first criteria. The second criteria, again, just to review, is that the limit as x approaches any number for the function, any x value for the function, that must also exist. And again, typically we're looking at certain x values, and a lot of times we're focusing on places where it's obviously discontinuous. But here, in any case, if I chose any x value in the function, the limit as x approached that number would exist. There doesn't seem to be any value here where I've got a gap or a break in the graph. And then the third criteria is that all the points that I have defined, f of a, must equal the limit as x approaches a of f of x. And basically that one's saying that I don't have any points that are bumped out of the graph. So from a very informal point of view, we would say that this function is continuous. So we'll make that claim. We in no way proved it, but just by kind of investigating the three criteria of the definition for continuity, we can informally, but pretty firmly say this is a continuous function. Okay, let's take a look at one more example. So our second example is a piecewise function. And a lot of times we see piecewise functions, and that's kind of a doorbell ring that says there's potential for discontinuity. So we'll graph this one, and it's two parts. So I do want to create a table of values with the two parts. So a lot of times the convenient thing to do is to give yourself 3 columns. And we'll put our x values in that left one. And the way I decide on my x values for the piecewise function is really that threshold where one function hands over to the second function. That's going to be the value 1. So I'm going to give a few values above, really to the left of 1. And then we'll also go with a few values to the right of 1. So we'll go out to 4. So I am going to note that this is the cutoff from one function to the next. And really the value of 1 belongs in the domain of the second piece of the piecewise function, since that's the greater than or equal to 1. But I will calculate it for the first one as well, since it will come up to that value and end at an open point. Well, let's calculate. So my first function here is -1. So recall, if you don't have a variable given in the function, it's constant, it's a flat line at that value. So all these values up through 1 and +1 are all -1. Now I'm going to circle that last one because that's an open point. This is strictly less than. So I'm going to go ahead and graph that. At -2, it's -1. -1, it's -1. And then there's an open circle. I'm sorry, let me keep going. I ended too soon. 0 is -1. The open circle is at +1. And then the graph for this is going to go along -1 forever towards -infinity. Let's calculate for that second part. So the second part is given as the function 2x minus 5. That's a line that has some kind of slope to it. So I'm not going to calculate these first values because that second piece to the piecewise is only defined when it's greater than or equal to +1. That's the domain for the second part. So I will begin calculating at 1. So this is 2 times 1 minus 5. So that's 2 minus 5 is -3. I'll go put that as a coordinate point. That's 1, comma, -3. Keep going. 2 times 2 minus 5 is -1. So that's the point 2, comma, -1. So it's definitely a line that's rising. It's got a positive slope. 2 times 3 minus 5 is +1. So that's the point 3, comma, 1. And then 2 times 4 minus 5, 8 minus 5 is 3. So we've got the point 4, 3. Let's graph those points. So 1, -3, that's our closed point, is there in quadrant 4. 2, -1 is also in quadrant 4. 3, +1 bumps up into the first quadrant, and then 4, 3 confirms that trend and carries us further along. In fact, that line shoots up into the first quadrant forever. So let's bring our definition of continuity. We finished that first task of graphing. So remember, we're looking at some specific x value. So with a function like a piecewise function, really where our attention is drawn is to that threshold. So we're saying we got a function f of x, and we're looking at x equals 1. So remember our 3 criteria for continuity. Number 1, f at 1 must exist. Well, I see it in my table. F at +1 is here as the value -3. So f at 1 equals -3. The second criteria is that the limit as x approaches 1 for the whole function must exist. And here we run into a problem. If I look at the limit around 1 from the left, the limit is -1. So I can write that out here. The limit as x approaches positive 1 from the left-hand side for this function is -1, because all the y values on that left-hand blue part of the piecewise, they're all at -1. Their y values are all -1. The right-hand side comparatively has a different limit. So the limit for this function as x approaches positive 1 from the right-hand side for the function f of x is not -1, it's -3. And recall, when I've got different values for my left-hand limit and my right-hand limit, what we would say is that the limit does not exist. And we can see here -1 does not equal -3 because the left-hand limit is different from the right-hand limit. We say this limit does not exist. And the way that that definition works is if you fail in one of the criteria, you really don't need to keep going. If one of the three criteria is broken, we would say that the whole function is discontinuous at that point. So we'll claim that this is discontinuous at 1. Now, in our previous segment, we did define 3 different kinds of discontinuity. So we should say, what kind of discontinuity is this? Well, notice that I've got finite values for my left and right-hand limits, but they're not the same. So let's zoom back up to the way we define stuff. So we had talked about 3 different kinds of discontinuity. And we'd seen a couple of these. We had seen infinite discontinuity, and we had seen a removable discontinuity on an example. Definitely what we're looking at is a jump discontinuity. So just again, to recap the way we describe jump discontinuity, a function has a jump discontinuity if the left-hand limit and the right-hand limit are both finite but not equal. And that describes what we're seeing here in our last example really well. I've got finite values for the left-hand limit's -1. And I got a finite value for the right-hand limit, it's -3, but they're not equal. So what we would say that this is a jump discontinuity. In fact, let's just change. We can be real precise with the way we're describing this. Instead of continuous, let's go ahead and say we've got a jump discontinuity at x equals 1. Well, thank you for joining for the second segment discussing how to determine function continuity or discontinuity. Just to recap that definition of continuity, a function f of x is continuous at a certain x value if the function exists at that value, if the limit of the function as x approaches that number also exists, and then thirdly, if the value of the function equals the limit as x approaches that number of the function are the same. Thank you for joining. I'm going to let you go work on some of your continuous, discontinuous questions. I will see you soon.